Okay, guys, I wanted to give you a couple of quick problems to help out with the homework. The first one is they're both about cars, and they're both about cars rounding curves. The first one is a car rounding a flat curve. So this is completely flat all the way around. And it says the radius of this curve is 50 meters. And they say that the coefficient of friction is 0.5. So mu s equals 0.5. In case you're wondering why it's static, even though the car is moving, the tire isn't rubbing against the ground. It's not slipping against the ground. The part of the tire that touches the ground is stationary. So it is static friction. So what we want to do in this case is do a free body diagram. So when the car is here, okay, my free body diagram says that you've got pointing inward the force of friction. Basically what happens is the car turns its wheels, and the direction the wheels are pointing determines the direction of friction. In this case, friction is the only thing that's going to be able to keep us headed toward the center. So this is mu s times the normal. And it is true there is up-down force as well. So this is a little funny because the up-down force would be into and out of the page. I can't really draw that. So I'm just going to cheat, and I'm going to draw it in this direction. This looks like it's tangential to the curve, but it's not. I mean this to be up and down. This is the normal force, and this is mg. And that's it. There's no other forces acting in this problem. And so we can say sum of the forces in the up-down direction plus n minus mg equals 0. So the normal force is equal to mg. And then in the centripetal direction, sum of the forces in the centripetal direction, we only have one, and it's mu s times the normal, and that is mv squared over r. We've got our centripetal acceleration here, okay? So I can replace this with mu s mg equals mv squared over r. And so you see we actually don't need to know what the mass is. Sorry, let me just get rid of this. Okay, we don't need to know what the mass is because it'll cancel. And you end up with v equals the square root of mu static times g times r. Boom. So relatively straightforward. I only had one force pointing in the centripetal direction. Okay, this next one's a little weirder. This next one, we're going to stay around the curve, but we're not going to use friction to do it. We're going to use the slope of a hill. So in other words, the circle is like this. If you ever watch Indianapolis 500 races or whatever, you'll see that the track they go around is sloped inward, and that's not by accident. It's designed to actually help them take tighter turns faster without slipping outward. So the question is, well, how does this push them toward the center? This is very strange, right? Well, if you look at the forces acting on it, there's no friction, so there's only gravity pulling downward, the weight, and then there's normal force, and that points normal to the surface. You can kind of already see what's happening. Part of the normal force, there's a component of the normal force that points toward the center of the circle. So in this case, the surface is pushing you toward the center the same way that when we talked about a roller coaster, the shape of the roller coaster pushes you upward, right? In this case, the shape of the track ends up pushing you inward because a part of the normal force lies in this direction. So I'm going to break this into two pieces. This is the normal force in the y direction. This is the normal force in the centripetal direction. Okay? And then, even though this problem seemed completely different, the math is going to look very similar. We've got sum of the forces in the up-down direction. That's equal to plus ny minus mg, and that equals 0 because it's not moving up or down, right? So this implies that ny, which is n sine of theta, equals mg, so that's good. Meanwhile, in the centripetal direction, we have n cosine of theta, and that's it. I don't have any other arrows. So that must be equal to mv squared over r. Okay. The normal force is mg over sine theta. So I can write, instead of the normal, I can write mg over sine theta. So mg over sine theta times cosine theta equals mv squared divided by r. And so you can see the math for this problem is almost exactly the same as the math for the other problem, even though the physical reason for the turning is exactly the same. We can plug in numbers here, right? I always put numbers in the problem. I'll let you plug them in. 30, 20 for the radius, right? So we get v equals, in this case, g times the cotangent of theta times r square rooted. Okay, so we have this. Now the question is, what happens if we add friction? Well, if we add friction, that's okay. Friction is going to point along the surface. So friction is going to point in this direction if we have it, right? Or it's going to point in this direction if we have it. Just like you have a component of the normal force that points in the centripetal direction, well, there's a part of the friction force that points in the centripetal direction as well. And so you'll just include this in your free body diagram, and you have a homework problem, which is pretty much exactly this with friction. So I wanted to show you what happens without the bank when you have friction, what happens with a bank without friction, and then your homework problem is to take these two things and add friction to the mix. You're not going to have to change it that much. You'll just have to modify these a little bit from the new free body diagram. Okay, I hope this is helpful. Email me if you have questions.